So last time I forgot to record the second hour. Then I had to shoot it again by myself. Okay, so last time we had started so-called mappings. Suppose we have a function, and suppose this is given as follows: f of p is equal to f1p fmp. So here little f1 to fm are just the coordinate functions. So each fi is a function from Rn into R, okay? Each fi is a function from Rn to R. These are called Euclidean coordinate functions of f. Okay. We talked about, I guess, so-called curve reparametrization, or no, composition of a curve with a function. Let me skip it for a while. And we also talked about derivative. So for any tangent vector, let's say this is a tangent vector to Rn at the point P. We have to put P, the point P here, but just to make life easier, we will usually skip it once it is understood, at which point the tangent vector is chosen. We defined the image of this vector under the derivative of f as the velocity vector of this expression. Okay, this expression at the point 0. So what we do the following. Here is, let's say, this is the curve f of t, p plus tv. Okay, when t is equal to 0, I am at this point, let's say, f of p, so t equals 0. And I just take the derivative of this expression considered as a function of t. So as t passes, I just move on this curve, and I take the derivative of this velocity vector of the curve at this point, and we call this vector f star vp. Okay. İsterseniz şunu şöyle yazsam belki daha iyi olur. Bu şöyle bir şey. Right? So this is the real line here at the point t. This point is mapped to via, let's say, f p plus tv to this point, and I take the derivative at this point. Okay, now this way, f star vp or f star can be considered as a function from the tangent space to Rn to the tangent space of, let's say, Rm, where Q is the point f of p. Okay, so Q is the point f of p. So it carries tangent vectors to Rn at the point P, two tangent vectors to Rm at the point Q. Okay, it is nothing but the derivative map. Okay, now let's see that actually. Here is the proposition. The expression of F star. Let me check if it is recording. Yes, okay. So let F be as above. I will usually denote it like this. Okay, be a map from Rn to Rm. Rm. If V is a tangent vector to Rn at P, then F star V is nothing but the vector P V, it's the function F1 and so on up to Fm. Okay, of course, you know, maybe I should put this P here. So what is this gadgets? These are just the directional derivatives of Fi's at the point P along the vector V, right? Remember that. So proof. Remember, what was this? Fp Vp of Fi. This is nothing but the directional derivative, right? Directional derivative of Fi at the point P along the vector V. So this is actually can be computed as follows, right? Dot product with the vector V, or I take this function, take its derivatives, compute it at the point P, and multiply this with Vj, sorry, J from 1 up to N, right? V is being a tangent vector to Rn, so it's a vector here and sent to a tangent vector at Q. So V has coordinates, let's say V1, V2, up to Vn. So that is the statement, okay? That is the statement. And let's see why this is the case. Well, this is of course just, you know, calculus. No. Okay. All right, let's see why this is the case. Well, let beta t to be this expression. Then, of course, this is nothing but what is F? F has coordinates F1, F2, Fm. So this is F1 of P plus TV up to Fm of T plus T, P plus TV. So the tangent vector, then the tangent vector mapped under the derivative of F. So this is by definition the derivative of F plus TV, right? Okay. Yok, yanlış yere döndü. O çok fazla döndü. So f of Vp is nothing but the derivative of f of p plus tv at the point t equals 0. Beta t is this, therefore this is nothing but beta prime at 0, right? Derivative of this expression at the point 0. So what is this? This is, of course, just, Leibniz rule. I just take derivative of this gadget. So this is just d dt of f1 t plus, no, sorry, p plus tv. And d over dt fm p plus tv. All this has to be computed at the point t equals 0. How would you take the derivative of this? Well, this is a function of several variables, right? The derivative of this composition is just you take partial derivatives of this gadget with respect to its variables. By the way, so let me just write here. What is, for example, fi, yeah, p plus tv. So this is just fi p1 plus tv1, right, up to pn plus tvn, right? P is the point here. P is the point p1 up to pn, and v is the tangent vector at that point v1 up to vn. And I take derivative of this with respect to t. So what we do, we just take derivative of fi with respect to each variable, and then I take the derivative of those variables with respect to t. So derivative of fi with respect to first variable, which is x1. So what I do, I just take partial derivative, and then I will plug t equals 0. When I plug t equals 0, I get the point p, of course, and then derivative of inside this gadget with respect to t. What is the derivative of this with respect to t? Of course, it is just v1. Here, summation, of course. Well, I have to do this for each variables. So I have to take summation from 1 up to n. And this will be done for each component. So fm del xj at the point p, v vj. Gradient times, right? It is nothing but the gradient vector times, it is this expression. Gradient vector times this. So, but, as I wrote here, this is nothing but gradient times the vector v. So it is just v. I feed it v with f1 and up to v of fm. And this finishes the proof. It is just, chain rule, nothing else but the chain rule. Sorusu olan var mı? Okay. If F Rn to Rm is a mapping then at each point P of Rn, the tangent map F star at P it takes tangent vectors to Rn at the point P and sends them to tangent vectors to Rm at the point Q is a linear transformation. Okay. Why is that? Yani şunu yapıyor bakın F so this is Rn, this is Rm, okay. Here is the map F and I am at the point P and it is sent to the point Q which is F of P. And what the derivative does is the following. It takes any vector here and sends it to a vector here, F star. At the point P, evaluated on the vector V, okay? Aslında belki evet şu notasyonu kullanmakta daha yarar var. Çünkü parantez içine V'yi koyuyorum. Yani F noktaları noktalara götürüyor. F takes points to points and its derivative map takes tangent vectors to tangent vectors. Okay, so as the differentiable function f takes points to points, its derivative takes tangent vectors to tangent vectors. Okay, and we claim that transformation at the tangent space, right? This is a vector space, this is another vector space. So this is a map between vector spaces. Therefore, you know, one may ask that whether is this a linear map? And the answer is yes. Okay, it's a linear map. So one must prove this following, must prove for this to be a linear map, F star P, and then if I take two vectors and add them up, then the images should be, you know, so V1 plus V2 should be F star, okay, şöyle yazıyorum, sorry, F star P V1 plus F star P V2. I have to prove this, and I have to prove also that I can take constants out. And I have to prove this. C times V is just C times F star PV. And that's not a big deal. Why is that? Well, we already computed, you know, this expression, so right? So what is F star P V1 plus V2? These are two tangent vectors at this point. Okay. At the point P, I have two tangent vectors, V1 and V2. I would like to compute this derivative. Well, we just computed that this is nothing but V1 plus V2 evaluated at the vector, at the function F1, V1 plus V2. No, here I have parentheses, Fm, but this is nothing but the directional derivative of Fi or F1 along this vector. So this is just F1 at P dot product V1 plus V2, and I can just repeat this for each coordinate, directional derivative of F at the point P, V1 plus V2, and that product is a linear operation in each coordinate. So I can write this as F P1 P V1 dot product plus dot product with this, and this is true for each coordinate. Yazı yazarken kolum ağrıyor. Herhalde 2 senedir tebeşir kullanmadığım için. And this can be written as what? This is the sum of two vectors. I take these vectors, this component, so del F1 P V1 del Fm P V V1, yes, plus del F1 P V2 dot product del Fm P V2. And this is nothing but F star at the point P V1, and the second one is F star at the point P V2. The other one, I will leave it as an exercise. So show this, show that F star at the point P, C times V, a constant times the vector V is just C times F star at V. Okay. This is not something we have for continuous maps, right? Continuous maps carries points to points. But if you have a differentiable map, then you not only carry the points, but you carry the vectors at that point, okay? That's something very powerful, actually. The reason is this, from the derivative map, you can read many properties of the function, and the derivative map is linear, therefore it is simple, okay? Understanding a nonlinear function, even quadratic ones, can be very, difficult. You know, from linear algebra, you characterize quadratic forms, right? There you have to use diagonalization and so on, right? It's a lot of work. So in general, understanding what a function does is not, something easy. But if it is differentiable, then it has a derivative map, and derivative map reflects several properties of the function, and the derivative map is just linear, okay? And you know linear algebra, therefore you obtain a lot of information. That's why, you know, derivative of a function is something very important, okay? And differential geometry is all about that, basically. Okay. Another corollary of all these is this. I guess we said somewhere that if I say f is a mapping, I mean it's differentiable, right? Because I don't write in my notes that it is differentiable. But mapping means differentiable, okay? We are doing differential geometry. Unless stated otherwise, everything is differentiable as many times as you need, okay? So we assume that. It's not, of course, you know, always true, but we assume that they are. We work with such functions. If beta is the image of a curve alpha in Rn, then derivative of beta is just f star of alpha prime. So what we do is this. Suppose we have a curve in Rn, and I have a mapping into from Rn to Rm, and the image of this curve is, let's say, this beta. So beta is just f composition alpha, and the claim is this. The claim is this. If I take alpha prime, a tangent vector here, its image, so that tangent vector, say this is the point P, yes, and this is the point, let's say Q, which is f of P, and that tangent vector is sent to the tangent vector of beta, okay? And actually it is given via this equation, okay? But of course, you know, this is also something trivial. Let's see the proof. Benim silgim. Şurada biraz temizlik yapalım. Okay, let's see if it works. All right. So proof of that corollary. Well, f has, let's say, coordinates f1 to fm as usual, and beta is equal to f of alpha. Alpha is, of course, what? Alpha is a curve in Rn, right? In Rn. Alpha is a curve in Rn. So alpha has coordinates, let's say alpha has coordinates alpha 1 up to alpha n, and beta has coordinates beta 1 up to beta m, But what are the coordinates of this? These are nothing but f is just f1 of alpha, fm of alpha. So beta i's are just fi alphas. Okay. So coordinates of beta are just f1 alpha, f2 alpha, fm alpha. All right. Thus, f star of alpha prime. I take alpha prime as a vector, as a tangent vector, right? Alpha prime is a tangent vector to Rn at the point P. So I am at this point. This is my tangent vector alpha prime. I consider this as a vector at the point P. And we have computed this. This is nothing but this is we computed that okay, so this is the vector. Yes, this is f1 alpha prime fm. Okay, yeah. Since this is the vector, f star v is just v evaluated on the function f1 comma v evaluated on the function f2 and so on. Of course, all these things happens at the point P, okay? I compute everything at the point P, but since alpha prime fi, this is nothing but the derivative of f along the vector alpha prime. So this is just actually the gradient, directional derivative of f along the vector alpha prime, and this is nothing but I may also write it this way: dfi of alpha t dt t equals 0. Değil mi? Bunun da türevini alsanız, what is this? Derivative of fi with respect to t, fi alpha t. We have done that computation over here. You know, consider this as alpha t. Bu kaçtı? 2 miydi? Yok. Okay. Consider this gadget P plus TV as your alpha curve, okay, as your alpha curve, P and then P plus TV. So this is your alpha T, F of alpha. And what is this derivative? It is just this expression, right? Just the directional derivative. So that's what we have over there. Okay, we have this. Therefore, this gives me the following. This is just df1 alpha dt dfm alpha dt. But what is this? This is just beta prime t, because beta is this expression, right? What is the derivative of this? You just take derivative of this gadgets with respect to t. Therefore, f star alpha prime is just beta prime. Okay. bunun bir sonucu olarak da şunu söyleyebiliriz. If f as usual this, then f star uj at p. So what is uj? I have Rn at the point P. At the point P, I have these vectors, U1 up to UN. What was UJ? UJ is this vector. It's a vector at the point P. It is the vector. We have 0, 0, 0, 1 here, and then zeros. This is the jth place. So I compute the derivative at this vector. What will be the answer? Okay, so yazdım şey. Okay, F star is this, F star VP. Here, instead of this V, I write UJ. So what is UJ? All the coordinates are 0 except the jth one. Therefore, in each summation, there are n terms, but all of them are 0 except the jth one. So we pick the jth term of this summation. The other ones are 0. Jth one is 1. All others are 0. Therefore, this is not just a sum, it's a single term because all others are 0. So it is just del f del xj times vj. Okay, so the first one is just del f1 del xj at p, and then well, I have this vj here, but the jth coordinate of uj is just 1. So I have 1 here because uj is this one. This is the first, so v1, v2, vj is just 1. And then I have all these up to nth coordinate. So del f m del xj at the point P times 1. Okay. All right. So note the following. This expression reminds us the following. This is a linear map. F star is a linear map, right? F star is a linear map from the tangent space to Rn to tangent space to Rm. And if you want to compute the matrix representation of this, what would you do? You take a basis here, and then you compute your linear map at the basis elements, and you represent them in a basis here, and then you look at the coefficients of the basis vectors, and you write them as columns, right? So here I take the basis u1 up to un. Here I take the basis again, let's say u1, but let me say it tilde, because these are basis vectors for Rm. These are basis vectors for Rn. Yani bunlar Aren'in standart bazı. 1, 0, 0 değil mi? 0, 1 vesaire. Bunlar da Aren'in. Bu da ne diyor? So this expression tells me that if I plug F star and write here UJ, so F star of UJ at the point P is this. What is this? This is nothing but del F I del XJ at the point P times UI tilde. Because you see, I can write it this way. Let me erase this part. What is this expression? This is nothing but del F1 del XJP 1, 0, 0, 0, 0 plus del F2 del XJ at P 0, 1, 0, 0, 0 up to del Fm del XJ at P 0, 0, 0, 1. These are tildes. U1 tilde, U2 tilde, UM tilde. Okay, so I have this expression here. All right, so this means what? In the matrix representation of F star in this basis, the jth column consists of this partial derivatives. So let me write that down. Hence, the jth column of the matrix representation of the derivative map F star, which is a linear map from the tangent space to Rn to the tangent space Rm in the basis with respect to the basis. Basis. Hangi basisler? Beta diyelim ki şunun basisi. Nedir bu basis? U1 up to UN and beta prime U1 tilde up to UM tilde. The jth column is what? Jth column is this. Del F1 del XJ at P up to del Fm yes, del XJ at P. So the matrix representation then, hence the matrix representation of F star in this basis is what? It is this one. So F star, the matrix representation of this, I guess you write like this, right? Matrix representation of F star at the point P, of course. Maybe I should also put P here. From this basis to this basis is what? The first column is just del F1, okay, del F1 del X1 up to del Fm del x1, and then del F1 del x2 up to del Fm del x2, and we go up to nth derivative, so xn del Fm del xn, and all these computed at the point P. Okay, all these derivatives are computed at the point P. This is nothing but the Jacobian matrix of F, right, with respect to these variables. Okay, of course, this is not something surprising, but that's what it is. The Jacobian matrix of F at P. Okay. So these are the vectors in at the tangent space Rm. I have m coordinates here. So this is u1 tilde, u2 tilde, um tilde. Nasıl? UC'ye apply ediyorum, evet. P noktasında ha burada summation I üzerinde. Dur. Summation m'e kadar, c birden n'e kadar. Tamam, tamam. M'e kadar. Tamam. Şimdi oldu mu? C sabit, I değişiyor. Birden m'e kadar. Tamam mı? Yani yaptığımız şey şu. So this is what we have done. I had this. I just wrote this, you know, in the as a linear combination of basis vectors. These are the coefficients. Basis vectors are 1, 0, 0, 0, 0, 1, 0, 0, and so on. Yani trivial şeyleri yazıyoruz ama trivial şeyleri yazmak tehlikelidir. Yani çok kafa karıştırır. O yüzden aslında insanlar böyle şeyleri yazmazlar. Peki. Actually, you have all done this in advanced calculus, right? I mean, this is nothing new. We just recall, but we, you know, regard them as different objects. Okay, let's give a break. After the break, we will continue.